Hi guys, so we're going to finish up with Lenotes because I got too excited talking about the ice skater. I'm here with Mia. Look at all these other science teachers. All right, so we're going to start. We're going to, what? We're going to go ahead and pick up on page 66. So this is where we left off. We were kind of freaking out because we said there is an angular acceleration of alpha, but there is no net torque. So we were wondering, what does this mean? Well, we figured out that net torque equals I alpha is valid, but only specifically when the rotational inertia of the object, or I, remains constant. So what made the ice skater speed up rotationally? It's when she brought her arms out, bringing them in, bringing her legs out, bringing them in. That changes that rotational inertia of I. Okay, so what we're going to do now is we're going to look at Newton's second law and Newton's second law for rotation. So they're the same thing. One's translational, one's rotational, right? We said that F net equals ma is our second law. Translationally, the second law for rotation is net torque equals I alpha, right? They go hand in hand. So what variables are constant, what can change? Well, if we look at the F net equals m times a, mass of the object remains constant, but the acceleration can change. When we look at net torque equals I alpha, for this equation to work, rotational inertia, we know that rotational inertia can change. As a result, then rotational acceleration also changes. And that's if net torque remains constant, okay? So this is a little bit different, right? Mass was constant for F net equals ma, and here in net torque, it's this whole new world. We're realizing that actually the I value can change, right? If I bring my arms out to arms in, I've changed that I value. So we're going to move on. So what does the original version of Newton's second law still hold for all of our situations? Well, mass is still going to be the same, right? If I go like this versus I go like this, mass of my object is still the same. The difference is that the rotational inertia of my object has changed based on where the distribution of mass now lies, okay? When we look at the equation, we're looking at F net equals m times a. If we just go down on this left-hand side of the column, we can look at everything translationally, and then we'll apply it rotationally. So translationally, we know F net equals m times a, which we can measure as delta v over t. And then we get the equation Ft equals m delta v. Now, if you remember, this side of the equation, F net times t and m delta v, this is where we came into impulse and momentum, right? P is equal to m delta v, and impulse is Ft. So we can read this equation in a sentence. We say if a force is exerted over a time, it causes, as a result, the object to change in velocity because mass stays the same, okay? So we take it to the other side with rotational, net torque equals I alpha. Just like F net equals ma, we can rearrange this equation, okay? We can say that alpha is really delta omega over t. That's just rearranging our equation of omega final is alpha t plus omega naught. And that leaves us with the equation net torque times t equals I change in omega. Okay, so if I follow the same thing that I did translationally, make this into a sentence. If a torque is exerted over time, it will cause an object to change its angular velocity. Now, this is only true if I is constant. Okay, that's going to be our stipulation, because we know that we can change I without torque. We can change the shape, we can change the distance from the axis of rotation of where that mass is located. So we want to keep that in mind. We want to make sure that we're keeping that constant. Okay, so we're going to take it one step further. And like we said, these equations show us what we know about momentum. Okay. In order for linear momentum to be conserved, there can be no outside forces. So P initial is P final. Okay. In order for angular momentum to be conserved, it's the same thing. Instead of no net force, there can be no net torque on the system, or no outside torque on the system. Okay. If there is no outside torque on the system, angular momentum will be conserved. And we're going to notate angular momentum as L, which is why we said like Lenotes. Okay, so we're going to notate angular momentum with capital L. So L initial is equal to L final as long as there's no outside torque on the system. Okay, so we've got our new equation, and that is net torque times T equals change in I times omega. That left-hand side, just like before when we broke down our linear momentum equation, the left-hand side is angular impulse, the right-hand side, angular momentum. Remember, we can use them interchangeably because impulse is momentum. They are one and the same, just depends on what variables you are given. Okay, so the only difference here, obviously, besides the fact of the variables being L and I and omega, is the units. So if I multiply I times omega, we're going to get I, which is kilograms meters squared, and then omega, which is radians per second. And we've talked about in our board meeting that radians really isn't a measurement that we have to continue to use. So we can multiply the units together to get kilogram meters squared per second, also known as Newton meters squared, or Newton meters times a second. This should match because net torque times time would be a Newton meter times second. Okay, so these are not the same as regular momentum. They are different units, but they still match, right? The angular impulse units still match the change in angular momentum units. So moving on, if we talk about conservation of momentum, right? We were freaked out because net torque equals I alpha was not working in terms of talking about the figure skater, but we can talk about it in terms of angular momentum and conservation momentum. So as my ice skater brings her arms out and brings her arms in, there is no outside torque. If there is no outside torque, then we know that there's going to be no change in angular momentum. So L initial will equal L final, and it will be conserved. So in order to make L the same, if we can break it down into I times delta omega, my I going from here to bringing it in, I have decreased my rotational inertia because I've brought my mass closer into the center. If I decrease my I, to keep L the same, we'd have to increase the omega, which is my angular velocity, which explains why when ice skaters bring their arms in, they spin faster and faster and faster. Cool. So we're going to turn on to the example problem. We're looking at a 50 kilogram person rotating on a stool, kind of like what we were doing in class. We've given you that they are their rotational inertia in the radius, and they hold 2 kilogram masses in their outstretched arms. So each mass is attached on each side of their body, and these are point masses. So we're going to assume that those point masses have an I equal to mr squared. So like we talked about in class, in order to calculate the initial momentum or initial torque on the system, you need to find the I of the system. So to find the I of the system, I'm going to add up the rotational inertia of all the pieces. So the rotational inertia of me, and then the rotational inertia of this mass in my hand, and the rotational inertia of this mass in this hand. So if I do 1/2 mr squared plus mr squared plus mr squared times my omega, I can calculate the initial angular momentum of the system, which if you see and look at my work here, we get 10 Newton meters second, okay? As the person initially has an angular momentum of 10 Newton meters per second, if they bring their arms in, the angular momentum still doesn't change. It should still be equal to the initial because there is no net torque. Their rotational inertia, though, has decreased because I've moved where the distribution of mass is from the outside to the center. And last but not least, if I'm keeping L the same and I has decreased, omega has to increase according to our equation, which is angular momentum equals I times omega. Okay? If you're still with me, we're going to continue on with some practice problems. You guys can go ahead and check your answers here. It's just giving you another scenario about where angular momentum plays a role, for example, in a diver. You guys can continue to find these problems 3, 4, and 5. The main idea being that if we're using conservation of angular momentum, if we know the initial, we know that's also equal to the final. So for number 3, when they ask us to find the final angular speed, if the initial L we said was 10 Newton meters per second, that's also the final L. I know my rotational inertia based on where my new radius of the masses is, and then I plug it in and I can get a final omega of 8.62 radians per second. That is much faster than my original angular speed, which was at 2 radians per second. So continue on with 4 and 5, and then we will pick up here in 1 second.